Yes? Okay, awesome. So I actually requested to go directly after Andre because I think our talks are great compliments. And yeah, I'm really excited to share with you on predictive representations, building blocks of intelligence. Yeah, I'm a fellow at the Chemistry Institute, and you can follow me on Twitter, CogSciKid. So I'm going to start with a question. How do we get intelligent behavior? And I'll give you at least one answer, which I'll focus on, which is good representations. So here is a kind of cartoon of an environment with a mouse in it. And when I use the word representation, I really just mean some encoding of either data or stimuli that that mouse will see. So a natural question is, what makes for a useful representation? So a representation is useful. At least one thing is that it describes different facets of the agent's experience. So for this mouse, it describes that there are berries and a pond and a snake and trees. Something else is that it describes what's good and what's bad. So for example, the water in the pond is good, and the snake is bad because maybe you'll get hurt from that. And then the last thing is a representation is useful if it enables making choices that allow an agent to repeat good experiences and avoid bad experiences. Right? So water is good, snake bad. Maybe also knowing where the mouse is in that map so they can take actions towards the good thing. So these are things that make for a useful representation. And the focus of this talk is going to be on representations that an agent learns through experience in the world. So what kind of representations should an intelligent agent learn? From what I've said so far, you might think representations that support classification, like this is a refrigerator and that's a stove. Maybe representations that support segmentation, so segmenting the car or maybe these children on the road. Now, at least from the perspective of artificial intelligence, these things have historically required labels. And it's not really clear where labels like that will come from. But what I want to focus on for the purpose of this talk is that these describe the present. They don't describe the future. So for example, the children or the cars, you as very clever humans may think that they're moving, but right in the scene, at least the segmentation does not say anything about the future of these things. Now, something else that one might want for representations are representations that support simulation. So this is produced by OpenAI Sora model, and it's typically really high def, but the internet is slower than the model itself. So it's a bit blurry. It's interesting. But you can see there's this dog climbing on this ledge, right? So this is like simulation. And so one might imagine that this is going to be really good for an intelligent agent, but there are some things to be wary of. So one is a simulation like this has the output of the simulation as input for the next iteration. So you get compounding model errors. And when there is uncertainty in the world, or stochasticity, the compounding model errors are exacerbated. The other thing is, for simulation, we probably care about distant futures. What happens if I go to downtown Rome? What happens if I go down the street? Things that are minutes, hours, days into the future. And it's very expensive to do simulation for that kind of long future. And so the argument I'm going to make here is that we want representations that enable evaluating choices in terms of their long-term consequences, like simulation, but allow for doing that efficient evaluation, and avoid compounding error. And so this brings me to my thesis, which is we want intelligent agents to learn predictive representations. And by this, I mean multi-step predictions of the future. So let's use this as an example. This is the mouse, and the present, it's over here. If it goes up, it will see berries and rocks and a pond. If it goes to the right, it'll see a bridge and snakes. So what are some things that are here? First is the mouse can describe its present by the future, right? If it goes up, it'll see berries, rocks, a pond. This can then be used to select actions, right? Do I go up and get berries, or I go to the right and potentially face the snake? Oh, I'll go up. So it's useful for selecting actions. And then the last, if you don't compute this iteratively, then you avoid compounding errors. So these are some nice properties of predictive representations. Okay, so why might predictive representations be building blocks of intelligence? So the first, if you can measure that a state leads to new parts of a state space, this can facilitate exploration. So here I draw your attention to the mouse over here, and from here the mouse is like, oh, I can get to trees from here. And from here the mouse is like, oh, I can get to trees, but also berries from here. But from this part of the state space, the mouse is like, oh, I can get to like the pond. And so this, in terms of like what you can reach from it, is different from these, and so the mouse may want to explore locally there. So this can help you with exploration. The other is, if you can predict that actions achieve multiple goals, then this facilitates composing goals. So let's say that this mouse, in its lifetime, has independently sought out berries and water and acorns, but at some point, it wants both acorns and berries. It can think to itself, if I go to the right, I can get both of these things. So facilitating composing goals. And then the third, if you can predict what states behaviors lead to, this can enable jumpy planning, right? So if I follow some behavior, I can get to berries. Another behavior, I can get to a pond. So jumpy planning. And these are at least 3 examples why predictive representations can be building blocks of intelligence: exploration, composing goals, and jumpy planning. Okay, but what kind of predictive representations support this? So the reason why I asked to go after Andre is because this is going to be the same family of algorithms that he was talking about. And it's going to be the family. I'm giving more of a homage to neuroscience, so I'm defining the family by the successor representation. Here I have a schematic of the diagram. I have a schematic of the environment from before. I'll use pi to refer to a behavior policy. It's a probability of actions given states. And I'll focus on the policy of getting these acorns. So the successor representation allows you to ask the following question. Starting at state S and following behavior pi, how much will I see different states? And so I've labeled the states, and it's basically state count predictions. Now, a generalization that Andre worked on is successor features. And this allows you to ask, starting at state S and following behavior pi, how much will I see different features? Right? So it's how much will I see the berries, or the pond, or the trees? And I'll explain the numbers to the left of this in a second. But these are feature count predictions. And then a third thing that is in the same family is something that me and collaborators are calling the successor model. And this is probabilistic and allows you to ask, starting at state S and following behavior pi, what's the likelihood of seeing different states or features? So this is like a probability you can sample from or evaluate. So these are 3 predictive representations in this family. And they all follow this basic form, and honestly, this is going to be the only equation of the talk. You have a prediction, y, that is, when following some policy pi, you care about something x. So it's a prediction about x when following policy pi, and what you're summarizing is the occurrence of some relationship phi between s and x. Right? So you have phi s1 x plus, it's going to be a weighted sum where the weights are these gammas, or these discount factors. Now these discount factors are going to be less than 1, and you're exponentiating them so they get lower as you go further into the future. And this is how you kind of formalize all of these predictions. It's a very general way. It ends up being really powerful, and I'll talk about it more in this for the rest of the talk. Now, you might ask, why have gamma less than 1? Going back to this intuitive example, here this is an infinite sum. So if you have gamma equals to 1, then a mouse will see everything at some point in the future. So you don't really get partiality about different actions or different policies if you have gamma equals to 1. It's also useful mathematically to have it less than 1, but at least this is some intuition. And so when you have it less than 1, then you prioritize seeing things more immediately. And then the second is, okay, why do we have this dependence on the policy? So the policy essentially defines the space of sequences that you'll be making predictions over. And so this allows you to kind of target the predictions over what features you care about. Some pros. This is unsupervised, so prediction targets come from future experience. That's nice. This is the algorithms for learning this are scalable. They can be learned with iterative temporal difference learning algorithms, so they can scale to real-world data. That's also really nice. And then these are very general. So this can capture structure in this form of equation, can capture structure in arbitrary sequences. So the pros of this are unsupervised, scalable, and general. OK, so let me now re-say my thesis from earlier. Agents should learn successor-like predictive representations because they capture structure in arbitrary sequences and can be learned iteratively. And for the rest of the talk, I will give you some examples of how this can be useful for exploration, composing goals, and efficient planning. Let me first talk about exploration. And this will be pretty high level, just to be upfront about that. So this is work led by PhD student Chris Huang. The basic idea of this work is we're going to use successor features to measure state novelty, and then we're going to explore around novel states. So it's just what I told you before. And just to give it a little bit more meat, so let's say that these are the successor features for different states, S2, S1, S3. These are the same ones from the example before. I just made up these numbers. It really is intuitive. This state over here will have different feature predictions for the ponds compared to these two. And so you're going to explore locally around here. And I'm very happy to talk about the details of the algorithm offline. So where was this useful? We use this to explore the Visdom environment without any reward. This is a maze. That's a very large maze. The agent gets images of this maze. It's a 3D maze. It just gets images. It doesn't know where it is. It doesn't have its location. And then it has to learn to map out and explore the maze with just images and no reward. And then at evaluation, we're going to give it a random goal image, and it has to get there. So this requires effectively exploring the environment. And the finding that we had in this work was successor features had better zero-shot transfer to novel long-horizon goals compared to methods that used Q-learning or Q-values. So again, going back to this maze, the agent always begins at this pink position. Green is easy, and you can see for easy, there's a relatively big gap. Medium is a little bit further away. The gap widens. We do worse, but the gap widens. And then orange is a bit harder, and red is even harder. And so you can see that this allows for effectively exploring this large map. That's the main thing I want to drive home. And evaluation to zero-shot evaluation to a goal image when it hasn't been trained on this. OK, now let me talk about composing goals. So the basic idea here is going to be as follows. So we're going to use successor features to dynamically select which goal composition to pursue. Right? So it's the same idea from before, but I'm going to give it a little bit more meat. So let's say that these are the feature predictions for going up. And I put random numbers here, one for the berries, one for the acorns. And then this is for action, for the first action. And for the other action, you have different feature predictions that are going to be around the berries and the pond. Now, you can have basically preferences over these that are state-dependent, that vary by state. So at this state, the agent wants the berries in the pond. Later on, it may want water and acorns. And this is a way that you can dynamically select goal compositions to pursue. We studied this in the context of transfer in the naturalistic playroom environment. So just to be clear, this idea originally is actually Andre Barretto's, so I want to give a shout out. And then I worked with Andre and Daniel at DeepMind to kind of scale this up to a large 3D environment. So we looked at transfer in this playroom environment. It's 3D. There are pixel observations. It's a pretty large state space because there are objects you have to interact with, and every single position of the objects is a different state in the state space. The agent gets tasks in a synthetic language, like place Teddy near cabinet. And the actions you can take are rotate its body and its head, It can pick up objects by selecting it on the screen, and it has to continuously hold them to move the objects. So that's kind of how it operates in this environment. And the challenge here was that prior work had mainly combined kind of go-to tasks, and we had these place tasks that have longer horizons, they're much longer, and the rewards are much sparser. So it's like a more challenging learning problem. So punchline, and again, happy to talk about the details of this offline, successor features enable transfer with 100 million plus fewer samples compared to transfer baselines. So for pre-training, the agent, like all agents, pre-trained on go to A and put A near B. And then there's like a fine-tuning stage where you transfer the combinations of this. So I have an example, put A near B, C near D, E near F. Now, if you have a curriculum of simpler transfer tasks, so for example, you learn go to A and place B near C as you learn this longer one, then we have like there's successor features enable like a relatively decent gap of like 100 million samples. But then once you remove this curriculum and you're just transferring to this much longer horizon thing, then this gap increases significantly, and one of the baselines really struggles to transfer here. Right? So the thing I want to drive home from this is using successor features allowed for transferring behaviors in a far more sample efficient way compared to other transfer baselines. Okay, and now let me go to the last part, which is efficient planning. So the basic idea is we're going to use the successor model to efficiently generate and evaluate plans of policy executions. So basically, plans are going to be composed of executing one policy, then another policy. So maybe the mouse is like, oh, first I'll execute the going to the bush policy. Then I'll execute the going to the pond policy. And what's cool about this object is that you can sample from it. And so you can sample some likely state when following that policy. So it's, for you, if you're familiar with Rome and you think to yourself, if I went to downtown Rome, what would I see? It's kind of like having access to an object that gives you that. And so you can do this for a bunch of sequences of policies, and then because of the math, you can efficiently evaluate these plans and then select the best plan. So that's the basic high-level idea. Okay, so just to be clear, this work is actually not my work. It's also actually Andre Barretto's. But it's a really cool example of successor model, so I wanted to highlight it. So they looked at planning to novel long horizon goals in the Mujoko ant environment. This ant had 4 policies it could do. It could move up, left, down, and right. And then during training, it could just learn the successor models for these policies in the environment to kind of capture the structure in the environment and what happens if I go in these directions. And then at evaluation, it has to plan a path to some novel, distant goal. Now, at least one challenge is that this is going to require long horizon estimation of the value of plans. Long story short with this figure is that having this jumpy planning allows for a much higher success rate here. And just to give a little bit of intuition for what's happening here, this baseline is basically like not jumpy in its evaluation of policies. And it starts here, the goal is here, and kind of meanders around. Whereas once you have jumpy planning with just plans of length 2, then you're able to effectively plan towards this long horizon goal. So successor models allow for this planning towards novel long horizon goals is the punchline here. So I'll come back to the thesis of this talk. Agents should learn successor-like predictive representations because they capture structure in arbitrary sequences and can be learned iteratively. In the first part, I first showed how this enabled measuring state novelty to systematically explore a large environment. Then I showed how this enables combining and staging goal-directed behaviors in a large-scale 3D environment. And then how this enables planning to novel long horizon goals via jumpy planning, so very efficient planning. And as a conclusion, I will conclude with next steps. What might this tell us about natural intelligence? One question is, Do we represent states with a successor representation-like object? Stackenfeld et al. Has some evidence that rats might, and there's other evidence that animals might. Another question is, do we compose goals with successor features? And Tomov et al. Has some evidence that suggests that we do. Another interesting question is, do we plan with successor models? There's no neuro or cog sci work here yet, but I think this is a really interesting question, especially because we really do seem to have the ability to kind of sample states from following a policy like this successor model does. And then the final one is the successor-like representations can capture structure in any sequence. Can they explain how we represent things like social interactions? And Rabinowitz et al. Suggest this is possible with machine theory of mind. So I'll leave it with these questions. And as my concluding slide, I've just released a kind of perspective and review on this family of algorithms, predictive representations, building blocks of intelligence, with Momchil Tomov, Wilda Kothi, Caswell Berry, and Sam Gershman. We talk about the theory, practical learning algorithms for actually learning them with real data, and AI applications, neuroscience applications, cognitive science applications. So if you want to learn more about this, please check this out.